So here are the topics that I would be covering in this presentation, from initializing and drawing board till the conclusion. Initializing and drawing board. So up here, I'm using NumPy because it better deals with 2D arrays. So to make an initial board shape, I'm using np.zeros 8 by 8, which basically makes the matrix 8 by 8, and u4 basically indicates that data type should be the string. And I have also initialized all the marker of both parties as well as how would be they be for the king. So the first challenge was that how would I draw the checkers as expected in real life? So I create a method initialize board which would run on every new game, and I'm importing the global variable board shape. X here up indicates the row, Y indicates up here column, and count is basically indicates that from where position should I start. As you can see the results, in 0 0 we have B, and then on 1 1 B, so count keeps take care of that, where should I place the B marker. And in the count method, as we are seeing, is that if the count is divisible by 2, place the marker up there. If it's not, place the space key up there. And if both of the statement is not agreeable, place the space key up there. And I'm doing this for every row and column, and the result is up there. And I saw a YouTube video. I have given the URL up there, and I saw these cool X and Y axes given on the sides of the board. They didn't show the solution, but I took it as a challenge because it will help me and any user to come to know what axes are they moving. So up here is it's simple. I'm as we know that X is the row. I'm getting the number and then attaching the whole one row print statement with the X, and same with the Y, and then I'm printing the whole board. And then in the end, I'm also printing how many checkers are out or have been taken by other party, verifying win or end of game. So there is basic two rules. Either there is no more checkers left, or there is no more moves for the checkers to make. So let's discuss the first thing. So I'm basically keeping trace of that if any of the checkers count parties, if any of the parties checkers count reach 12, return nothing for the side turn. Side turn basically keeps in check whose turn it is. So the moment anything reaches 12, it will it won't allow another side to make the move. So the game would stop up there. The second thing up there is no more moves available for any checkers of a party. So I created a method called no more moves. So before I give the power to any party to make move, what I do is that on the board, on the current board, I check that whether the king version of that marker has any available positions, and if they do have, check the moves of those available position. If there is even one available move for any of the checkers, return false. Then I give the power of that party to make the move. And if it comes that no more moves returns true, then I just return the print statement and the side turns uh, ends the function. Moves and jump. The second challenge that I faced was that how would I simulate the checkers moves and jumps. So I got 4 pictures up here. So let's start with the main function picture. So available moves handles all this case. It basically accepts x and y axis of the current marker and which marker we are dealing on the current instance of the board. Available moves stores all the legal moves. O marker and O marker basically decide what's our opponent markers. Direction basically decide in which direction our marker would be moving. For example, black checker, a simple black checker can move only in downward direction, whereas the white checker can move in upward direction, and the kings can move anywhere. Coming back to the first step. So here I basically decide that if the marker is a black or a white checker, a normal checker, run these functions, and if it's a king checker, run these function. and has been a slight modification in the x-axis and the double x-axis because they can move in both 1 and -1 direction. In the second step, I'm basically calculating the y-axis with the direction and verifying whether the moves they are making are inside 0 and 7 because our length of the board is 8. I'm also checking that if the next step is empty, then I'll add in the available moves, and if next space is accompanied by the opponent marker, check the next space direction of that checker whether it's an empty or not. If it's empty, run the dy-axis function and add it in the available moves. In third step, we are verifying the double jump. So I'm doing the slight modification. I'm basically repeating the first and second step, no more than that. Whose checker got out? This was far the greatest challenge for me in to bring this functionality out in the game. Why? Because whenever a checker makes a move, I'm only getting two coordinates. One is the old x-axis and the new axis. I have to actually calculate which direction is it going and whether it's a single jump or a double jump and which checker is it trying to take out. I know you're feeling overwhelmed with these many pictures and line of code, but I applied some simple mathematics concept to solve all these cases. So let me explain you. So whenever there is a move, we have 2 points, the old axis and the new axis. I find the difference between them and check which axis is greater, whether the new x-axis is greater or the new y-axis is greater or the old axis is greater or the old y-axis is greater. Why? Because the difference between the x-axis or the y-axis tells me what jump is it. Is it a single jump or a double jump? A simple jump would have a difference of 2, whereas the double jumps would have the x difference of 4 and the y difference of 4 if they are going diagonally. And if it's on the same x-axis or the y-axis, the same axis would be 0 and the other axis would be 4. And why I check that whether one axis is greater than other, to check whether the direction what's the direction of that the checker is going. So I better can decide which checker to take out. So once I know the direction, what I do is that I get the position of the checkers that we are going to take out and store in a variable. After storing in a variable, I send to do a method called checkout counter, which keeps track of the numbers of checker which have been taken out. That at the position of that checker which is been taken out, I replace that checker value with the blank space. After doing that, what I do is that the checker who's taking out this checker is sent to the new axis and the old axis is replaced with the blank checker. So in my strategy, I'm using two functions. The first function, the formlet shape, basically accepts the positions available for my black checker. And what I do is I hardcode and try to make an X with a pyramid shape. In the third picture, you can see that I am successfully able to make a X shape with a pyramid shape. And in case there is a jump available in front of my two pointers of X at 3 1 at 3 3, it will try to jump and take over the other checker. In case it successfully forms and there is no hurdle in between, I run a random choice method. What random choice basically does, it calculates whether there is any jump available or not. If there is any jump available, add it to the jumps move dictionary and return the coordinates with the maximum jump. And if there is no jump available, then do a random choice for any available musician. That basically means is move any checker at random. With this strategy, I'm always attacking first. So let's perform now Monte Carlo simulations and see what are the results. So up here, what I'm doing is I'm setting the number of games that I want to play as 1,000, and I have three trivial strategies that I'm going to play against: fixed row, X shape, and pyramid. So I have set the ANS is equal to 1, so that up here in the end I'm always playing against the fixed row strategy. So let's see what are the result. So let's play against the other trivial strategy, that's the X-shaped strategy. So I'm setting the ANS as 2. And so we can see that we win around 993 games and we lost 7. The accuracy of winning is 99.3. Now let's play against the third strategy, trivial strategy, that's the pyramid strategy. And up here, I would set the debug truth. So let's just see the board printed. So we can see that I won around 998 times and I lost 2, and the winning accuracy was 99.8. Conclusion. So in the game, I didn't apply the Minimax algorithm as I talked in the project proposal. This project is not stable, it crashes in between while performing the Monte Carlo simulation, and I have to modify some of the rules. For example, it's not mandatory to select the first capturing move, it's optional. No, in this game, no checker can make more than 2 jumps in one move because of the programmable constraints that I was limited to. Overall, for me, it was kind of like a second capstone project. Lessons learned. So I was quite stuck in some of the problems and always feel frustrated why they weren't getting solved. But the moment they get solved, I find this some kind of happiness that always motivates me to go for the another challenge. So I believe that challenges do provide sustainable happiness. And if you're like me, that some of the functionality wasn't completed, so just remind yourself that I haven't failed. I just found 10,000 ways that won't work by Thomas Edison. I'm pretty sure I learned so many ways that I shouldn't have wrote my programs. So this is all part of learning. And thank you, sir, for teaching me this course. It's been a really pleasure. Thank you, everyone, for watching this video. Have a good day.